Good evening, Bertha. Thanks for coming out tonight. As you probably know, this talk was originally scheduled to occur last month, and while it is always my intention to have my audience blown away by my talk, we had high winds last month, so the talk was rescheduled for this month. So I'm Greg Wirth. I'm with company BAE Systems, formerly known as Ball Aerospace, based down in Boulder, a company that started off building equipment for space exploration back before NASA was even in existence in the 1950s, and has continued working. How's the sound? Good? Okay. I will hold the microphone like this. BAE Systems has continued to build spacecraft for NASA for virtually every NASA astronomy mission from the earliest days right up to the present, and will continue doing so in the future, as I'll talk about tonight. So before we get started, I always like to get acquainted with the audience. How many folks here are engineers? Excellent. Okay. And how many astronomers here? Excellent. And of course, you think I'm being kind here, trying to get to know you, but I'm just trying to find out where the difficult questions are going to come from, so I know where not to call. And so with that in mind, do we have any fifth graders here? Okay, I'm safe. Good. Yeah, right. Okay, so tonight I'm going to tell you about some of the space telescopes that the company has been involved with and is going to be involved with in the future, including the Webb telescope, the upcoming Roman Space Telescope, and the Habitable Worlds Telescope.
These seem to be a lot cleaner, aren't they?
Oops, there we go.
How this goes, and just to adjust the volume.
Thank you. How's that? Great. Okay, we'll go handheld. So let's talk about space telescopes. But first, a few words about my background. So I grew up in the Great Lakes state in a town that proudly calls itself the Chemical City, home to a major chemical company which has brought the world Ziploc bags, styrofoam insulation, and silly putty. And despite the cold and nasty winters there, I got interested in astronomy. My indulgent parents bought me this telescope that I still own to this day that got me started in astronomy. And telescopes have been a theme through my life. I ended up at a university on the north side of Chicago that was home to the world's largest telescope in 1865 with a whopping 18-inch telescope. I then went on to Santa Cruz, California, and got to use the world's largest telescope back in 1888. That was the 36-inch Lick refractor, and eventually ended up out in Hawaii working with these two telescopes, which are still the largest pair of telescopes on the planet, largest optical telescopes, the Keck telescopes. I was at Keck for 16 years, came here to Boulder about 10 years ago, and have now been at BAE Systems for 7 years. Okay, so starting off to talk about space telescopes, the first thing we want to talk about is Hubble, which was, of course, the most famous and beloved space telescope before the James Webb Space Telescope was launched. Hubble has been orbiting since 1990, just past 35 years of service last year, still doing great science, orbiting 350 miles above the Earth's surface every 90 minutes, and it's been used for thousands of observing programs, from my Hubble thesis project to the famous Hubble Deep Field survey that redefined how we study the universe. And my colleagues at BAE Systems, some of whom are here tonight, it's great to see, are exceptionally proud that our company has built all 5 of the science instruments that are currently on the Hubble Space Telescope. So we feel like we have a big stake in this observatory. Now, Hubble has done fantastic work and has given us many beautiful pictures, but Hubble is more than just a machine for making exceptional, beautiful images of the universe. It has taught us about how galaxies form. It has taught us about how stars evolve and explode in titanic explosions that strew gas and dust through space and then that glow afterwards in the light of oxygen and nitrogen and sulfur. Hubble has taught us how galaxies like our own Milky Way formed and evolved, how some galaxies occur in groups that interact and merge, and how some are torn apart in interactions that strew gas and dust throughout space. But Hubble has an important limitation, and that is that it does not see all the colors of light that exist in the universe. When we look at a rainbow, we are looking at all the colors of light that our eyes can see, from red on through blue, but there's more there than meets the eye. If you go beyond the bluest light that we can see, you enter first the ultraviolet, and then if you go further, you go into X-rays and gamma rays. And it's this region where the Hubble Space Telescope really excels. It is exceptionally good at observing ultraviolet light from space that does not reach the ground, and also observing in the visible light. But you can also go the other direction. You can go past the reddest light that we can see. And if you do that, you enter first the infrared, and then microwaves and radio waves. And it's this regime that new space telescopes have exploited, and specifically the James Webb Space Telescope is specially designed to observe the universe in the infrared. So these are all different kinds of light to scientists, even though we refer to them by different names. It's all light. Okay, so why would you want to observe the universe in different kinds of light? And the answer is because you get different information. Here's a constellation that is probably familiar to everyone in this room. It's one that adorns the night sky above us. If it clears off tonight, of course, we'll see it. And this is Orion. And what we're seeing here is the view of Orion that we get with our naked eye. And virtually everything you see in this picture is a star, with the exception of the Great Nebula there in Orion's belt. But if you had infrared vision, you would get a completely different view of this part of the sky with your eyes. Instead of seeing stars, what you would see would be the glowing clouds of hydrogen gas that are left over from the Big Bang and that are forming some of the stars that we see in Orion. So infrared vision allows us to see things that are out there in space, but that are not apparent to us with our visible eyes. Also, infrared light can penetrate through clouds of gas and dust to show us what lies behind. This is a picture of a particularly interesting part of the sky that's within our Milky Way galaxy. This is a nebula. And if you look in the middle of this nebula and you focus in on that, you're looking at a particularly interesting part that has these features that some people have referred to as the elephant trunks. And the largest of these are so large that they're 1,000 times larger than our own solar system. So these are big features. Well, Hubble observed this and made one of its most iconic images. So iconic, in fact, that if you go in the restroom here in the back, it's on the wall. That's how iconic it is. Okay? This is the Pillars of Creation, one of the absolutely most beautiful images to come out of Hubble. And what you see here are clouds of gas and dust, nitrogen and other elements there. And you see some young stars. Now, young stars are usually blue because they're hot, but these young stars are red in appearance because the light is passing through clouds of gas and dust that preferentially removes the blue light and allows the red light to shine through. But if you look at this nebula in infrared light, you get a completely different view. Here we see thousands of stars that were previously hidden behind the clouds of gas and dust, but they're now revealed to us because the infrared light can penetrate through the clouds and come to us. So observing the universe in infrared light allows us to see things that are out there that are hidden, but that become visible to us when we can see through the gas and dust clouds. The most important aspect of any telescope is the size of its main mirror. A larger mirror gathers more light. That allows you to see things that are fainter and thus further away. And this image compares the size of the mirrors on two famous telescopes. It compares Hubble's 2.5 meter main mirror to the much larger 6.5 meter mirror on the James Webb Space Telescope. And just as a point of comparison here, the previous best telescope that NASA had flown in space, the Spitzer Space Telescope, has a main mirror that is smaller than even one of the 18 segments here on the Webb telescope. This is why Webb is so powerful compared to anything that came before. Now, to give you a sense of scale, over here on the right, we have a full-scale mock-up of the Webb telescope. You can see the primary mirror there, and below that is this 5-layer sun shield that acts like a sunscreen with an SPF of 1,000,000 to protect the telescope and the instruments from the light of the sun and keep them cold so they can observe the universe without interference from infrared light. Webb is the most sophisticated observatory ever flown. That technology goes into everything from the instruments that analyze the light to that amazing sun shield. But the heart of the telescope is these segments that make up the main mirror. So let me introduce you to 3 of the key innovations that allowed the Webb mirror to revolutionize how we do astronomy. First, a little about the telescope. Webb is a reflecting telescope. Its main mirror points at targets in space, collects the photons coming from those targets, and reflects that light to first the secondary mirror and then on to the tertiary mirror that corrects for astigmatism. After a few more reflections, the light enters the instrument within the telescope. And the instrument is basically a fancy version of this thing that you carry around on you. It has a sensor in there that accepts light and that outputs a digital image that the astronomers can analyze. That's the basic of how the telescope works. Okay, now let's get back to that mirror. 3 things about the mirror. First, if you'll note, there is it's not a single piece of glass. The mirror is made up of 18 hexagonal segments that have to work together to act as a single piece of glass. Breaking the mirror up like this allowed us to launch the telescope because this 6.5-meter mirror was too large to fit within any rocket that was available to us at the time the mission was planned. But that meant that once we launched the telescope, we had to be exceptionally careful about aligning those segments so that they act like one unbroken piece of glass. They need to be aligned to a tolerance of about 1/10,000th the width of a human hair. Okay, so exceptionally close. So the mirror is made up of segments. That is the first innovation that allowed the Webb telescope to succeed. Now, what about the material that goes into the mirrors? Here on here on the ground, we build mirrors typically out of glass, whether they're used on the Keck telescope, a ground-based observatory, or whether they're like Hubble's mirror. We typically use glass for mirrors. Glass has great properties. It is very strong. It is very stable. When it changes temperature, it maintains its shape. So glass is wonderful, but glass is also heavy. And building the Webb telescope mirrors out of glass just was not feasible. It would have weighed too much for us to fly it. So we needed a solution. We needed a different material. And the solution was to use metal. Now, metal is normally a terrible thing to make a mirror from. Metal has the wonderful property that conducts heat very well, but that typically means that it will change shape if the temperature changes. And these mirrors are manufactured here on the ground, but up in space, they're in an environment that's close to zero, absolute zero. So we couldn't use a normal metal. But after much research, my colleagues who worked on the program identified a specific metal that turns out to be ideal for that purpose. And it's not some exotic composite or carbon fiber. It's right here on your periodic table. Element number 4, beryllium, a relatively rare material that is mined at one American mine in the state of Utah. It turns out to be wonderful. It is I believe 6 times stronger than steel, but lighter than aluminum. So it has these wonderful properties, and it tends to maintain its shape. It holds its shape very well, even if the temperature changes, as long as it's in a very cold environment. So beryllium is a wonderful material for making a space telescope mirror from. The mirrors on Webb all started off as these 5-inch thick slabs of solid beryllium weighing about 550 pounds. And we took those hexagonal slabs and we used a computerized milling machine to hollow out the backside of the mirrors, reducing the mass from 550 down to just 45 pounds, and leaving behind a 2 millimeter thick skin on the front that could serve as the reflective surface. After polishing that front surface to perfection, we coated it with 18-karat gold. Why gold? Well, it turns out that most of the mirrors that we encounter in our daily life are coated with aluminum. When you go in the bathroom in the morning and you look at yourself, you're looking at an aluminized surface. And aluminum is a great material to reflect visible light, but in infrared wavelengths, it's only about 85% efficient in reflecting light. In contrast, gold is 98% efficient in reflecting light in the infrared. So it's the ideal material for making infrared mirrors. And just for perspective, this layer of gold is only a few atoms thick. So the entire amount of gold needed to coat the segments on the Webb telescope would just about fill a single golf ball. That's all you need. So, the third key innovation is making mirrors that can move in space. And for that, we had to do some interesting mechanical design. This is an image of the back of one of the Webb mirror segments. And what we're seeing here are these things called actuators. There's 6 of these hexapod actuators that can move the mirror side to side. They can tilt it up and down. They can also rotate the mirror clockwise or anti-clockwise and translate it up and down, left and right. And there's a 7th actuator in the middle that's connected to the edges of the mirror, so it can pull on the edges and actually change the shape of the mirror. And it turns out that you need all of these ways to manipulate the mirrors in space remotely in order to align the segments perfectly so they act like one unbroken piece of glass. And they need to operate in the absolute 0 or 40 degree Kelvin temperature of space in a perfect vacuum. So these are really mechanical marvels. And this is the third technical innovation that allowed the Webb telescope mirrors to function. I could give you an entire talk about the interesting things that our team did to focus the telescope on orbit, but that's a talk for another night. Suffice to say, Webb is doing amazing science, and we'll come back to some of the scientific discoveries later. But just for perspective, this is an image that the Spitzer Space Telescope, NASA's previous best infrared telescope in space, took some time ago. And this is the same region of space imaged with Webb. You'll notice that things that are just fuzzy blobs with Spitzer are resolved to pinpoints of light with Webb. Things that are completely invisible to Spitzer stand out easily with Webb. This is why it's so powerful and why astronomers are so excited to have this tool to study the universe with. So we'll come back to Webb later in the talk to share some of its findings, but now I want to move on and talk about another space telescope, which is the Roman Space Telescope. So it turns out that Webb is basically a Swiss Army knife for astronomy. It can do many different kinds of things, but it's specialized to look in certain parts of the sky very deep. In the decades since Webb was designed, we've learned interesting things about the universe. We've learned that instead of expanding infinitely after the Big Bang occurs, we expected the expansion of the universe to slow down over time because of the gravitational tug of all of the galaxies within the universe. But 20 years ago, it's getting on toward 30 years ago now, astronomers made an interesting discovery, which is that at some point, the universe actually starts speeding up in its expansion. And that means that there's something about the physics of the universe that we needed to understand more fully. And in order to do so, we need telescopes that can do observations differently than Webb and Hubble can. So at this point, we believe that the amount of normal matter in the universe, the things made up of protons, neutrons, electrons, and neutrinos, totals only about 5% of the mass energy density of the universe. That's not very much. What else is out there? Well, we think another 27% of the mass energy density is in the form of dark matter, a form of matter which interacts with normal matter gravitationally, but gives no other evidence that it exists. We can't see it, we can't feel it, and it only appears to manifest itself on the scale of galaxies and above. That leaves another 68%, which is in the form of a mysterious force that is causing the universe to expand more and more rapidly. And this is what we refer to as dark energy. And we are just beginning to understand, to explore what dark energy could be about. So the purpose of the Roman Space Telescope is to address dark matter and dark energy. How do we do this? Okay, well, we can study dark matter by exploiting one of the predictions of Einstein's general theory of relativity. Einstein told us that anything that has mass distorts the space-time around it. So when light passes through an area of space that's occupied by a massive thing like a cluster of galaxies, that mass will act like a lens and distort the images of things that are behind them. So when we use our telescopes to look at distant galaxies that are far away, and that light travels to us through an intervening group of galaxies, it will distort the images of those distant galaxies into arcs and blobs. We can measure those distortions, and from those measurements, we can infer how much mass is in this cluster of galaxies, and that gives us a handle on how much dark matter there is there. We can repeat that over large parts of the sky and map out the three-dimensional distribution of dark matter. And as Mark mentioned at the beginning of the talk, because telescopes are time machines, they allow us to see back into earlier eras. That allows us to map out how dark matter is changing over time. Is it becoming more prevalent, or is it disappearing? That is a key clue that will help us understand what the nature of dark matter is. Now, what about dark energy? We explore dark energy by using some of the most energetic events in the universe, supernova explosions. When certain stars reach the end of their life, they tend to explode in these titanic explosions where the light from a single supernova can outshine the light of an entire galaxy of billions of stars. For example, back in 2010, the Hubble Space Telescope observed a supernova explosion in a distant galaxy. This is the galaxy right here. This little smudge is a galaxy that could be as large as our own Milky Way, but is so unimaginably far away that it is reduced in size to just a few pixels in the image here. In October of 2010, Hubble saw a new point of light there that is a supernova explosion occurring on the outskirts of this galaxy. Well, physics tells us that when these supernova explosions occur, they should release the same amount of energy no matter where they occur and no matter when they occur. That means they can act as a yardstick that allows us to map out the universe. You can make a diagram. You can plot how bright a supernova appears to be from here on Earth versus how far away it is. We know intuitively that as we take a candle and we move it further away, the candle gets dimmer. And the same is true of supernova explosions. But there's an interesting effect here going on. It determines the nature of the dark matter and dark energy will determine what the exact shape of this curve is. So for example, the dotted line here on top shows the prediction of how supernova brightness will change with distance in a universe that contains only normal matter and no dark matter or dark energy. The middle curve shows what happens if there is a certain amount of dark matter, a lesser amount of normal matter, not enough to close the universe. But this bottom line, the solid line, shows the prediction for a universe that contains both normal matter and dark energy. And you can see that the points here that represent measurements of supernovae closely track the line that has dark energy. This was our first clear indication that dark energy existed. The goal then is to get more and more measurements of supernova here, many thousands of them, so that we can make more precise measurements and get a sense of how dark matter is evolving and dark energy. So we needed an observatory that is capable of finding thousands of supernovae and exploring large parts of the sky to map out dark matter. And that is the purpose of NASA's next great flagship observatory, the Roman Space Telescope, pictured here. Roman will combine the monolithic mirror technology of Hubble with the infrared vision of Webb to create a powerful new observatory. NASA has named the observatory for Nancy Grace Roman, NASA's first chief of astronomy, who in the 1960s advocated for putting a large telescope in space, earning her the moniker the Mother of Hubble. So the power of Roman, the reason it will be so innovative and allow us to do new and exciting things, is that it has a new type of array detector that is far larger than anything that was available on Webb or on Hubble. So in fact, the Roman Space Telescope will be able to see areas of the sky that are 100 times larger than what can be seen with Webb or Hubble. Each image with Roman covers 100 times as much of the sky, and that means that Roman can survey the sky 100 times faster than Hubble or Webb. BAE Systems built the main instrument on the Roman Space Telescope, the Wide Field Instrument. This is a picture of the filter wheel on the instrument. The filter wheel has various filters that allow the camera to take pictures of the universe in different colors of light, including infrared light. The filters are equipped with these interesting masks. These masks are shaped to block out the instrument's view of the telescope's secondary mirror and its support structure, which emit infrared radiation that would otherwise contaminate the science images that the instrument is trying to take of the sky. This is a picture of Dr. Greg Mosby of NASA, who's at Goddard Space Flight Center. He's one of the detector experts, and he's holding in his his left hand here, that's a large cell phone detector, the thing in your phone that takes an image. And over in his right hand is the far larger detector that will be used in the camera on the Roman Space Telescope. And Roman will have not just one of those, it will have 18 of those massive detectors. So each image that it takes will generate 300 million pixels worth of data, which is a lot. Just to put that in perspective, over its first 30 years of operation, the Hubble Space Telescope generated 172 terabytes of data. Now that's a lot. That's a lot of data, and astronomers are glad to have that. But in just the first 5 years of operation, Roman is going to generate 20,000 terabytes of data. It's going to be a massive treasure trove of stuff to explore.
Sorry, I just wanted to ask, you can't possibly go to that organic, or where do you store all this? How many years like that? You can't lose it.
So the question is, how do you process that amount of data? Yeah, well, astronomers back in the day used to just very carefully look at each image and milk it for all it was worth. The analysis of data from the Roman Space Telescope will be highly automated. Computers will identify supernovae as they explode. They will automatically detect and measure galaxy shapes. So we'll be using modern computers and perhaps artificial intelligence to automate the process, because you're right. It's way too much data for a single person or team to deal with. So after several years of work, we delivered the Wide Field Instrument to NASA about a year ago. NASA has now integrated that into the Roman Space Telescope, and next month the entire telescope will go into the final thermal vacuum testing that it needs prior to launch. Now, if you recall, the Webb Space Telescope didn't exactly finish on time. It was famous for having been years behind schedule and many billions of dollars over budget, which absolutely nobody in astronomy was proud of. But the Roman Space Telescope has learned lessons from what was done on Webb. And it was originally scheduled to launch in 2027. It is actually on track to launch this fall, almost a year early, and it is on budget. So we're very proud of the fact that this is a demonstration that NASA knows how to carry out these flagship astronomy missions, even on schedule and within budget constraints. Let's now turn to the future. Yes.
One question about Roman. What kind of orbit will it be in? Where are you going to put it?
Excellent question. Roman will be in the same location that the James Webb Space Telescope is. We'll be launching it out to the L2 position out beyond the moon, where it will be in an Earth trailing orbit. Yeah. Okay, now let's talk about the future. So Roman is going to do exceptional science, but recently we have discovered many thousands of exoplanets, actually over the last couple of decades. We recently passed 6,000 exoplanets that are known to us. And the Habitable World Space Telescope will be an observatory designed to answer a single question. Is there life on other Earth-like planets in our solar neighborhood? So this observatory will be used in the visible and ultraviolet to take images and spectra of planets orbiting other stars. The key technologies here are so daunting to develop that this observatory will actually not fly until sometime in the 2040s. So many years of work are going to go into developing the technologies for this. There are two main goals for the Habitable Worlds Observatory. The first is to take direct images of Earth-like planets around stars that are within our area of our galaxy, to be able to see them for the first time directly. And then to be able to study the atmospheres of those planets for signs of habitability and potential evidence of life, including things like oxygen and ozone and other things that we associate with life here on Earth. HabWorld is going to rely on two key technologies from previous generations of space telescopes. It's going to need to collect as much light as possible in order to be able to spot the feeble amount of light coming off the planets going around other stars. And for that reason, it's going to need a large mirror, which probably will need to be segmented just like the Webb telescope. Also, it's going to need a starlight suppression system to be able to see planets despite the light coming off of their parent stars. And that is a job for an instrument called a coronagraph, like the one that the Jet Propulsion Laboratory has built for the Roman Space Telescope. So a little more about the coronagraph and what it does. Being able to see even a Saturn-sized planet around a nearby star is exceptionally difficult. The reason is that, of course, planets don't give off their own light. They shine by reflected light. And the dim planet tends to get lost in the glare of the parent star. Well, the coronagraph can basically create a temporary solar eclipse around that distant star, blocking out its light and allowing us to see the faint light of the planet nearby so that we can take an image or a spectrum of it. So this is a simulation of the first goal for the Habitable Worlds Space Telescope, being able to take a direct image. The current generation of telescopes, including Roman, may be able to see things like Jupiter and Saturn, but those aren't the places where we expect life to occur. We need to be able to see smaller, rocky, Earth-like planets like Mars, like Earth. And those sorts of planets, they're smaller and thus dimmer, and they're closer to their parent stars typically, all of which makes them very difficult to see. Telescope like the Roman Space Telescope is equipped with a coronagraph that can see an object 1 billion times fainter than its parent star. But in order to be successful in taking images of Earth-like planets around other stars, we need to up that to at least 10 billion contrast factor between the parent star and the planet. And to do that, we need to create a telescope which has optics that are incredibly stable. So in order to illustrate how these telescopes will improve over what we do today, take a look at this diagram. So this diagram shows basically how easy it is to detect planets around other stars. There are two factors that affect the detectability. One is the separation of the planet from its parent star. A planet that is further out away from its parent star it's easier to escape the glare of the parent star, which makes it easier to detect. And the second factor is how bright the planet is compared to its parent star. A larger planet will reflect more light, so it will be higher in this diagram and easier to see. So the upshot is that things in the upper right corner here are easier to detect. Things down here in the lower left are harder to detect. And there are some lines on here. These lines represent how far down in the diagram various telescopes that we have today can go in terms of detecting these planets. They don't go all that far. Even the best telescopes like Hubble and Gemini peter out around halfway down this diagram, which is a logarithmic diagram. Each major tick mark is an order of magnitude, a factor of 10 in terms of detectability here. So they can see some of the Jupiter-sized planets that are out far away from their parent stars, but they do not penetrate further down, allowing us to see closer Jupiters. The goal for Roman is to be able to see Jupiter-sized planets that are at distances of about 10 parsecs from Earth. And this will be a key accomplishment for the Roman coronagraph after it flies. However, that's still nowhere near good enough to be able to see an Earth-like planet around a nearby star. In order to do that, we need to go much further. And that is the goal of HAB worlds, to be able to push the limits of detectability all the way down here to where Earth is. And that means getting hundreds times better than what we can do today and what Roman will be able to do. Okay, so the key here is making a telescope with incredibly stable optics. And in order to make the optics incredibly stable, you need to be able to measure the positions of those optics to incredible precision. And so one of the technologies we are pursuing is being able to measure the location of one segment on the telescope relative to its neighbor. Here on Earth, telescopes like Keck have been addressing this concern for decades using something called capacitive edge sensing, where we have an electrical system here that can measure minute differences in position between two adjacent segments. This on Earth gets you down to maybe 100 nanometers. But in order to be successful in space for the HAB Worlds mission, we need to push this down to the level of 10 picometers. That's 10,000 times better than what Webb was able to do. Another key thing we need to do to measure the positions of the optics is to be able to measure the position of the secondary mirror of the telescope relative to the primary mirror. And for that purpose, we're developing what's called a laser truss that uses a system of laser emitters and sensors to be able to measure the tip, the tilt, and the separation between the primary and the secondary mirror, again, to exquisite precision. So, as I said, the Webb Space Telescope, its mirrors are aligned to roughly 100 nanometer precision. And in order to succeed, HAB worlds will need to get 10,000 times better, down to the level of a few picometers, which is less than an atom in terms of how accurately we need to measure the sizes. That is 1/10,000,000th the diameter of a human hair. And this is a daunting technology. We are working on ways to do this. We believe it is feasible, but we have several years of research and development ahead of us in order to be able to demonstrate to NASA that these technologies are workable so that NASA will agree to fund the development of this next great observatory. Okay, I promised to bring you back to Webb. And now I'd like to share with you some of the things that your tax dollars have paid for in terms of the discoveries that Webb has returned to us since it launched just over 3 years ago. Webb has given us some great views of things within our solar system, like this amazing view of the planet Neptune, surrounded by 6 of its moons, including Triton here, which actually outshines even the planet Neptune here in the infrared. Webb has given us images of the aurora on Jupiter. This is the glow caused when charged particles from our sun are funneled by Jupiter's magnetic fields into the polar regions, where they strike and interact with the trihydrogen atoms and cause them to glow. These aurora on Jupiter are many times brighter than the northern lights that we get here on Earth. Hubble gave us an image of this beautiful nebula, which contains a star that is accumulating mass and will someday turn on. And stars that have already turned on and are emitting copious amounts of energy that are evaporating the nebula that it originally grew from. Webb has shown us images of stars that are in their late dying stages. Here we have a star that blew off its outer layers over 1,000 years ago, where these rings, smoke rings basically in space, are continuing to expand, creating this beautiful nebula. In this recent image, we have two galaxies that are aligned. In the foreground, this greenish glow is the foreground galaxy. We talked earlier about gravitational lensing, and it turns out there's a galaxy in the background which is perfectly lined up with this foreground galaxy, causing the background galaxy to be magnified and gravitationally distorted and creating this beautiful image. And Webb is showing us clusters of galaxies filled with arcs and blobs representing more distant galaxies that are also gravitationally lensed. Okay, I'd like to go deep into three key scientific discoveries that have come out of Webb since launch that I think find particularly interesting, starting with some discoveries about stars. There's a particular kind of star called a Wolf-Rayet star that is exceptional. So this is a Hubble image of one of these stars, WR124. These stars are nearing the end of their life, but they are like blast furnaces in space. They can be something like 100 times more massive. They can be many times more luminous and 30 times hotter than our sun. So these are exceptional objects. And Webb took interesting images of this particular object called WR140 in 2022 and then again in 2023. And if we take a segment out of this image and compare the image taken in 2022 with the one taken in 2023, what you notice is, first of all, there's some interesting stripes here. All right, what's going on? What are these stripes all about? These are not artifacts of some camera. These are actually shells of dust surrounding these stars in space, which is rather interesting. Not something we normally see around a star. And by looking at the comparison between these images, we see that these stripes are not lining up. What we're looking at here are shells of gas and dust, and the fact that they have moved over the course of a year tells us that they are expanding, and not expanding slowly, expanding at 1,600 kilometers per second. That's 1% of the speed of light. So what's going on here? Well, astronomers have considered what could be causing this, and here is the image, here's the idea behind what they think is happening. They think this is actually a system of two stars that are on an orbit that every few years brings them close enough so that the prodigious winds coming off the stars will interact and form carbon grains that then get blown out and emitted in these shells. And we think this actually may be how these stars are seeding the universe with the carbon atoms that are necessary to support life here on Earth and perhaps elsewhere in the universe as well. So this flips back and forth between the two images taken a year apart. And with your eye, you can see how these shells are expanding over the course of just a few months. So this is not something we normally get to see out in space. The things changing over the course of just a year. More recently, Hubble took images of another Wolf-Rayet system and captured these beautiful images. And here is a simulation that explains what we think is going on. We think this is actually a system that contains not two, but three stars, including two Wolf-Rayet stars and a supermassive giant star. And they're on orbits such that every 25 years, when they get close together, they create another one of these dust shells. So what we see here is what we would be able to see if we could zoom around this star system in a spacecraft and take a look at it from all different angles. We see that there are at least 4 different dust shells here, the largest of which is over 4, almost 5 light years across. And this is just another example of how when we look out in space, we see things that we didn't expect to find. So stars, they can be interesting. Who knew? I talked earlier about the HabWorld's mission and its goal in searching for life. There were headlines made last spring about a possible discovery of life or signs of life on another planet made with the Webb Space Telescope, which surprised many astronomers. And this was associated with a planet called K218b, discovered with the Kepler spacecraft that BAE Systems built for NASA and which flew about 15 years ago. So K218b is a planet going around a star that is not that far from us. This is the Milky Way galaxy. Our sun is about 2/3 of the way out from the center of the galaxy toward the edge. And the Kepler mission was looking toward the center of our galaxy when it discovered this planet. The planet is about here, so you can see it's more or less in our neighborhood. And astronomers reported that there were potential signs of life here, which got news organizations very excited. There were breathless headlines about the possible discovery of life. But let's take a look at the data and see whether we believe that this could actually be the case. First, a little background here. The reason the Kepler spacecraft was able to discover this planet is that it's on what's called a transiting orbit, where the planet will pass directly between the parent star and our telescopes here on Earth every so often. And when it does that, it creates a mini solar eclipse, dimming the light from that star ever so slightly, but enough that we can detect the change in light and determine that there's a star there. Every star has an area where it can support life. Okay, so if you take a planet and put it out in a random part of space, it's most likely going to end up in an area where it is too close to its parent star to support life because the water will boil off, or too far away and the ice will all freeze. But there is a zone that depends upon how bright the star is and how far away the planet is from the star. There's a zone where liquid water can exist. And of course, we're lucky that Earth is in the habitable zone for the sun. And it turns out that this planet K218b is more or less near the habitable zone for its parent star. So it's not out of the question that there could be life there. Okay, so what did the astronomers actually do? So they took data on this planet. I mentioned that the planet comes between the parent star and Earth. That means that when it's doing that, when it's in transit, some of the light from that star is passing through the planet's atmosphere. And when it does that, that light will carry with it the signature of the chemicals that are in that planet's atmosphere. We can take the light from that star that has passed through the planet's atmosphere. We can put it through a device called a spectrometer, and we can see the chemical fingerprints of the elements in that planet's atmosphere. That's what these astronomers were trying to do. We've seen this done before. And for some reason, this is disappointing. Well, sorry, the graphic is not working here, so I'm going to have to do a little tap dancing here. Well, it worked in the run through earlier. Let me wander back here and interrupt the reboot. We're not going to reboot, but I am going to interrupt and restart this in the hope that it will bring it back to life. If I can just pass through here for 1 minute, bear with me. We're going to just start once more. There we go. Okay. Thank you very much. Unplanned foray into the audience. So this is what a spectrum looks like. Okay, a spectrum shows how much light you see from something as a function of, this is basically color on this axis. And this is how astronomers study the universe. And the power of this is that it allows you to see chemical signatures in the atmosphere of a planet in this case. This is an example of an exceptional spectrum. This is a spectrum of an exoplanet that the James Webb Space Telescope took of a super Jupiter planet, much larger than Jupiter, called WASP-39b. And what we see here, see this bump here? I should explain. See all the white dots, okay? The white dots are the measurements. And the white dots have little bars up extending above and below them. Those are the uncertainty or the error associated with the measurement. And then there's a blue line here. This blue line is a prediction of what this planet's atmosphere would look like if it had carbon dioxide in it. And you can see there's excellent agreement between the white dots, the measurements, and the blue line, the prediction. This tells us that this is a very high quality detection of carbon dioxide in this planet's atmosphere. This is a believable result, okay? Let me compare that then with what the astronomers saw in K2-18b. Now put on your scientist hat here for a minute and think about what is different here. First of all, you'll notice that there are many fewer data points. We're dealing with a sparser amount of data. You'll also notice, look at the size of the error bars here. The uncertainty in the data is much greater than it was in the WASP-39b spectrum. And then look at the agreement or lack thereof between the white dots, the measurements, and the predictions. Okay, it's far from a slam dunk here. The astronomers are claiming that there's dimethyl sulfide in the atmosphere of the planet based on this data. But somebody pointed out that, yeah, you could take a straight line and fit it to the data, and it would be just about as good a fit as this fancy predicted spectrum. So the upshot is that the astronomy community is skeptical about the reality of this discovery. We are left with Carl Sagan's quote that extraordinary claims require extraordinary evidence. And I think most astronomers would agree that we're not to the point of seeing the extraordinary evidence we would want to see for life on other planets through that spectrum. That's not surprising. These are incredibly difficult measurements. These astronomers should be lauded for trying, but I think the actual discovery of life on other planets is going to need to await the Flight of Habitable Worlds Observatory down the line to be able to make more definitive statements about that. All right, now let's turn our attention to galaxies. So last year, NASA released this fantastic web image of galaxies. We see these systems of billions of stars everywhere in the sky, and they range in size and shape. We have things that are spiral galaxies like our Milky Way. We have things that are red elliptical galaxies like these things down here. And there are other types of galaxies too, like this assemblage of blue light coming in here. This is actually a galaxy that's very close to us within our local group, a dwarf galaxy, one of the most common types of galaxies in the universe, but so diffuse and difficult to see that this particular galaxy, even though it's on our doorstep, was only discovered 15 years ago. So one of the reasons we built Webb was to be able to help understand how galaxies form and evolve. And this is an example image that the Webb telescope took of a cluster of galaxies. The galaxies here in the main cluster are about 6 billion light years away. We are seeing them when the universe was about half its present age. And that is a good way back to the start of the universe. But these are not baby galaxies. These are fairly mature galaxies. But it turns out in this image, if you look closely, you see actually 1, 2, 3 little faint red galaxies. And it turns out that those 3 galaxies are actually the very same galaxy that is appearing here in 3 different spots because of this gravitational lensing effect that Einstein predicted. So this is one of the earliest galaxies in the universe. Being seen with Webb. And as Webb has continued to look for galaxies, it found this particularly interesting object, which astronomers called the little red dot, because that's what it looks like. Well, it turns out, as Webb has looked more and more, it has found these little red dots in profusion. These are interesting because these galaxies are completely invisible to us in visible light. They give off no optical light. They can only be seen in the infrared. And so the question is, what are they? Well, we've now taken images of several of them, and the interesting thing is that they show no spiral arms or other structure here. They're really just points of light that appear to exist early in the universe. So, in order to understand what they might be, you need to take a spectrum. in order to find out what the composition of these is. And the Webb telescope spent 60 hours, an incredible amount of time, looking at just one of these little red dot galaxies and got the spectrum here shown in black. And for comparison, the spectra of normal galaxies are shown down here below. This galaxy does not match the spectra of the traditional galaxies. In fact, it looks more like a single super hot star than it does to a galaxy. There's a tremendous drop-off in the amount of light here in the visible versus in the ultraviolet. So what is going on here? What could it be? Well, this has given rise to an interesting suggestion that what we're looking at in these little red dots is a new type of star called a black hole star. You take a huge cloud of gas, and in the middle, you put a supermassive black hole. That black hole puts off prodigious amounts of energy from the accretion disk of matter that's falling into it. But that energy is then absorbed and re-emitted by this surrounding ball of hydrogen. So it's like a super big star, but not a traditional star that has fusion going on in the middle to power it. It has a black hole in the middle that is creating this energy. And just for comparison, this would be much larger than any star that we've ever seen, perhaps the size of our entire solar system. And so this is one possible explanation for what could be causing these little red dots.
Black holes suck up more energy than they leave out. How is it still burning, and how did it not instantly collapse?
Okay, so we think what's going on here is that the energy is actually being given off by this matter that is surrounding the black hole in this so-called accretion disk. This is where the matter spirals in and eventually gets consumed by the black hole. And that is what is emitting the energy here. And it's that energy that is then flowing out into the hydrogen gas, where it is then re-emitted from the outer layer and just looks to us from our vantage point billions of light years away like a super, super bright star. Okay, so we've talked about 3 different missions here. Webb is the telescope of today. Roman is the telescope of the near future, and HAB Worlds will be our legacy to the next generation of astronomers. Those of you who are youngsters here, your career, if you end up being an astronomer, may be defined by using Roman, using Webb, and eventually using HAB Worlds to study the universe. If history is any indication, when we turn these telescopes on the universe, we will make discoveries we haven't even thought of today. And the wonderful thing here is that this is not some billionaire's vanity project. This is the product of your tax dollars being put to good use to do great science. So thank you for the work you have done to make these discoveries possible. Thank you very much. All right, I'll take a few questions, but in the recognition of time here, yeah, okay.
First thing is, there's not a lot to see out there right now. So ask all the questions you can come up with. Like you want, well, yeah, they just want.
There's a young lady here who has her hand up. Yes. Oh, sorry, in the blue dress.
Go ahead.
What exactly are black holes?
Oh, what exactly? See, as I told you, I should have. It's great. Okay, so black hole, that's a great question. A black hole is a super dense object, so dense that it has so much gravity that not even light can escape from it. No matter comes out of it, no light comes out of it. It is so dense that it just will not allow anything to escape from it. So it appears black because we can't see any light from it, even though it can be incredibly heavy, incredibly massive. We cannot see it because no light can escape from it. Yes.
My question is, but the light that we see from, I always use the expression, it's all those atoms that are being sucked into the black hole screaming for help.
Yeah.
That's the light that you see coming from that accretion disk.
All right.
But in space.
It's
you
not
can't
coming
hear
from
it.
inside the black hole.
And folks, I should introduce my colleague Paul Lightsey here. Dr. Paul Lightsey was one of the key players on the James Webb Space Telescope. So he's come here tonight, and I'm using phone a friend to help answer the difficult questions from the audience. So thank you, Paul, for coming here. Yes. Yes.
Do you know anything about the Great Attractor?
The Great Attractor. Okay, now that's a blast from the past. So, just for benefit of others in the audience, back in the 1980s, it was discovered that if you looked at the red shifts of galaxies, they were not all expanding away from us uniformly. Okay, there was a certain area of the sky where galaxies appeared to be pulled into a certain area of space by a putative region where there was a super dense collection of galaxies that was causing an anomaly in the velocity flow. And there was a theory that there was this big collection of galaxies that was affecting the Hubble flow, the flow of galaxies away from us. And, you know, to be honest, I have lost track of what eventually happened to the Great Attractor. Does any of the astronomers in the audience remember what happened to the Great Attractor? I think as we got more and more data on galaxies and their flow, I think it was eventually determined that the Great Attractor may not have been as great as we originally thought. I think that's where it went. Yes, a lesser attractor. Okay, yes.
To the extent that there's any dust out there in space, do the mirrors get dirty?
Ooh, do the mirrors get dirty? Well, they get damaged. Yes. So that's an excellent point. So shortly after Webb launched, we had a program of monitoring the focus of the telescope very carefully, and every so often, every few weeks, we would see that something had happened to the mirror. Some micrometeoroid out there, you know, incredibly small thing, maybe the size of a big one might be a grain of sand, but probably much smaller than that typically, would hit the mirror and leave an imprint. And so that is the typical thing that happens to the mirrors out there. We don't really worry about them getting dirty per se. There's not a whole lot of dust that would coat the mirror in the solar system. But the more interesting and dangerous thing is the impact of micrometeoroids that could damage the mirror. And we've actually seen it create divots in the mirrors, and that's likely to be the limiting factor in the lifetime of the telescope. Eventually the mirrors will get so dinged up that they won't focus as well as they did originally. Yes, Paul?
Could I just comment though?
Yep.
The residual dust from clean rooms and everything else that we've tried to clean off of them causes more scattering than what we will have from the micrometeoroid effect over a 10-year lifetime.
There you have it from the expert. Okay, yes.
So dark matter, isn't it a really big assumption that there's just this magical substance that we can't interact with except for gravity to just like fill in 95% of the universe? Isn't that a huge fold? And could our theory of the universe be completely wrong?
Yes. So we know there's something out there that is binding together galaxies and clusters of galaxies. If you look at a cluster of galaxies and measure how fast the galaxies in it are moving, physics tells you that it should fly apart. So there is some binding force, some binding thing that is keeping these clusters of galaxies together. And we call it dark matter. We believe that it exists because of the gravitational effect it needs to have to explain the existence of these clusters of galaxies. But we have no clue about its nature beyond the fact that it creates gravity. As I said earlier, we think it's 20-some% of the mass energy density of the universe out there. But beyond that, we don't know if it changes over time. We don't know very much about it at all. So that will be the challenge for the next generation of astronomers, is to use these telescopes to study that. All right, you've been very patient with me. I'm happy to take more questions up here.
Something about science and hypotheses and everything else, right? So the dark matter and everything is part of the hypothesis.
Yes.
So now what we're trying to do is, well, collect evidence. If you want evidence, you prove your theory.
What you're touching on is a key difference in astronomy. Right? Astronomy is an observational science. Unlike, say, physics, where you can build an accelerator, you can do a test in a lab against a hypothesis. In astronomy, you use your understanding of physics to try to guess what you're going to see. Then you go look, you say, that's not what we see. So you go change your model, and then go, is that what we see? So you can only observe because you can't go run a test. The universe is so big, the scales are so large, the energy is so high, you can only guess and then compare when you observe it from the
Scale
scale.
of right too, right?
Yeah, fun.
Brings these, and a real good example of that would be observations of M1, Paragon Nebula, right? And how it does change shape, but to us, it hasn't changed that much in the last 25 years.
Speaking of observation, I have a question about a potential type of observation. I understand about the Einstein lensing and so forth. You've seen galaxies. To your knowledge, has anyone observed a supernova in one of those galaxies? And what does it look like?
So great question. The question is, have we observed supernova explosions within a gravitationally lensed galaxy? I believe the answer is yes. What does it look like? It looks like there's a brightening of the area where the supernova occurs, just like there would be in any normal galaxy, and then a fading as the supernova fades. But the image of the galaxy is distorted, and so it's possible to see supernova even in gravitationally lensed galaxies. Yeah, great. Folks, thanks for coming out tonight. I don't want to keep you here any longer than you need to, so feel free to come up and ask me questions.